It's important to do that. Exponents and solving equations. Again, you guys are going to be able to solve equations in the form of a to the x equals b to the y, and use laws of exponents to simplify. Now we just reviewed, I believe, all of the laws of exponents except for one. So the next slide that I go to, it has an example there for every single one of your laws, but in all honesty, you guys do remember this, right? It might have slipped your mind for a second, but once it started coming, once we started saying it, started coming back, correct? Okay. So everybody knows the big number is called your base, and the small number at the top is called your exponent. It also calls your power, also called your index. Okay? Different names for that exponent there. Here are your laws. You have the product one that says when you multiply, you add. You have your quotient one, which says that when you divide, you subtract. You got your power law, which says that when you have a exponent raised to another exponent, you multiply. You have your inverse law that basically says when you have a negative number, you got to make it positive, so you flip it basically. And then of course your zero power, anything raised to zero power is 1. You guys said that you remembered all that. Okay? Now the one thing that wasn't mentioned is that when you have a fraction as an exponent, it can actually be written as a radical. Okay? The denominator of that exponent is the index or the root of your radical. And then the numerator stays on the inside with your base as the exponent. Okay? I realize B can never be 0 because you can't have a 0 root or anything like that. And nor can B be 1 because you can't have a first root. There's no such thing that starts with square root. And you don't. And we all know that when it's a square root, we don't actually put the 2 in the index. You remember that, right? Like square root is just right with us. Okay. For what? These are called rational exponents. Yeah. Rational exponents. Because you have your fraction as an exponent. Just remember that the denominator is your index and the numerator stays with the base. Okay? Well, any questions about this? Yes?
I'm sorry, I know you just said it. Can you repeat the name of that law?
Oh, rational exponents. Alright? We're going to look at some examples, okay? Not some, several, okay? Now I want you guys to work on this. You're going to apply your laws, okay? And to simplify these next several expressions, okay? I'm going to give you about 8 minutes to do it, okay? That's why I said several, not a few. Few means 3 or 4, several means 7 or more, okay? So you got several. And I want you guys to work on them, compare answers, and in about 8 minutes we're going to go over them, okay? See how well you guys can simplify these expressions. Every single one of these is separate, so you got one here. In total. Okay? 8 minutes. Alright, so here we have a power on the outside, which means that you have to cube everything on the inside, including the 2. So hopefully you had 8x cubed y to the 6. You guys have that? You didn't forget about the 2? Awesome. Here, that 1/2. Remember, give a fraction to exponent can be written as a what? As a root. What's the root? It's the square root of 36 to the first power, which is just 6. 2. Raise your hand, 2.
Wait, wouldn't it be positive negative 6?
That's only if it's an equation. Oh. So it's just going to be the positive 6 here. Over here, you're doing the same thing. Now, 1/27 to the 4/3 can also be written as a root. What root is it? Cube root. 1/27 to the 4. Now, hopefully, you did not do 27 times itself 4 times.
I tried to.
It gets a little ridiculous. Well, that is one way you do it. You could do 27 to the 4th power and have 1/whatever that number is, and then take the cube root. Or and then apply the exponent. What's the cube root of 1 over 27? 1 over 3. So if you can raise that to the fourth power, it should be 1 over 81. So that's number 3. We're racing.
Wait, isn't it?
What's the negative do? To the 6. Makes it a fraction. So this is really 1 over 6 to the positive 2. So you should have 1 over 36. Same thing with number 5. But this time you have a fraction that's raised to the negative power. So what do you have to do to that fraction? Put it under 1. And when you put 1 over a fraction, what does it do to the fraction? It flips it. Reciprocal. Turns the exponent positive, and then you square the top and the bottom. 4 squared is 3 squared is, and there's number 5. So this is 3. 5. Ooh, what about this one? 5d to the 0.
5.
It is 5. Because only the d is raised to the 0 power, so only d turns into the 1, and you just get 5. What about 7? It would be 6 over x cubed, because only the x is being raised to the negative third power, not 6x, just the x. That's kind of tight. Number 8 was 2x squared cubed, which is
387.
8x to the 6.
I was looking at the wrong one. I was looking at
8x to the 6. Over here, we're going to take the cube root of 27, 8 to the 6, which turns into 3x to the second. Very good. And the last one, you got to do a couple of things. Because not only do you have to, negative means flip it, but we also have to take the square root of it. So we need to flip it. And then the 1/2 means we're going to take the square root. And we take the square root of a fraction. How do you do that? Do it to the top and then to the bottom. What's the square root of 16?
4.
Square root of w to the 4th. And square root of 9. And square root of b squared. And there's 2. Anybody get 10 out of 10? You. Start off strong. That's how it is. 9 out of 10? 8 out of 10. I just need a little refresher dust off the dust. Dust off the dust.
Number 6 is 5.
Yes, because only the d is being raised to 0 power.
Oh, true.
So you can write exponential equations in the form of a to the x, b to the y. Okay, where you basically have a base with the respective exponents equal to each other. And this is one of the easiest ways to solve exponential equations when you're not allowed a calculator. The trick is you want to get the left side and the right side of the equation to have the same base, because when you do, all you have to do is set your exponents equal to each other. All right, so you have to solve 3 to the x minus 1 equals 3 to the 5x. Again, one of the easiest ways to solve this without using your calculator is make sure that the bases are the same, because if they are the same, like in this example, you can just get rid of them and set the exponents equal to each other and solve. So what's that? Subtract over x, divide by 4, and x is a negative 1/4. Okay? You can always check to make sure that it actually works out by plugging in. And in this case, since the bases are already equal to each other, what's negative 1/4 minus 1? And what's 5 times a negative 1/4? So it shows that they are going to be equal to each other because it's 3 to the same exponent. Over here, is there a way we can rewrite 81 to have a base of 3? 3 to the 4. Knowing your powers can definitely help you out with that so you're not struggling. And now with the bases being the same, you just set your exponents equal to each other and solve. Subtract 1, divide by 3, and x equals 1. Double check and plug in. What's 3 times 1? Plus 1 is 3 to the 4th, 81. No. Over here. This is a little different. Can I rewrite 24 to have a base of 3? No, we can't. But if we notice, is the x in our exponent? No, it's right just side by side with 3. Okay? So we're really just solving for x. I ain't gonna say like normally, like how we normally would, but we won't be able to use like this trick that we use for the other two. So how would you suggest we solve for x? Anybody? Remember, the number one rule when you're solving equations is you want to get the variable by itself. So since it's being multiplied by 3, you divide by 3, which is 8. And now that we just have our variable with our exponent on the left side, how do I get rid of my exponent? We can use our negative rule, meaning yep. So we flip it, make it positive. Now what? Not square root. Not cube root. You have the fifth root. But it's technically in the denominator now. And so we really can't fifth root it like to both sides. That makes sense. Yes, you could. But I got a question, do I do that here or do I do that back? Step back. So, there are two ways you could have done this. I was going to roll with this one, the first one I heard. Okay? You could keep solving this. And then I'm going to address yours. How would you solve this? How would you get the variable out of the denominator?
You multiply both sides of that variable.
So you have 1 equals 8x to the 3/5. Then what? Divide the 8. And then what? You could take the fifth root. Do you know what the fifth root of 8 is? No? It is a weird decimal. So this is where what Jessica said is actually going to be very helpful. And we could have actually done this back here at this step. To get rid of the exponent, you could also raise this to the reciprocal. As long as you do it to both sides. It's an equation, so whatever you do to one side, you can do to the other. So if you raise this to the 5/3 power and you do it on both sides, huh? It gets rid of it. And that's really what you need to know is that when you have a rational exponent and you're solving an equation, you can always get rid of that rational exponent by not multiplying, but raising it to its reciprocal.
So over on the beginning, we got x with negative. We do it by negative power 3 or by power?
Negative. And then you just deal with the negative back there. Okay? Running out of space, so I'm going to change slides real quick. So I have 1/8 raised to the 5/3 equals basically just x. I still got this 5/3 thing here, but what can I do now? it back at this step. The one thing you would have to do before you actually do the cube root will be to what? Flip it. Before you actually went about doing it. Okay? So you go either route, but at some point in time, you're going to have to you're going to have to raise your exponent to the reciprocal. And that's really what I'm trying to get across to you guys. That's another way to say it. Questions? Awesome. Try this one on your own. There are a few things here. The 2 is the only thing being raised to the x plus 1 power. So you can't multiply 2 in a into the 2 to get 16 to the x plus 1 power. It's only 2 being raised to that power. Okay? But one thing that you can do is that because it's 8 times this and 2 times the square root of 2 to the x, you could kind of deal with the 8 and the 2 if you would like. Okay, that is one way that you can do that.
So you can do 4 times 2 the x plus 1 is equal to 2 to the square root of 2x.
You can do that. You divide everything by 2. Okay, the only thing that's affected is the number on the outside. This is being multiplied. Okay? Now, did anybody try to change this radical? Did you think about doing that? It would definitely make things a lot easier because that way you're only working with a base of 2 and not a base of the square root of 2. Does that make sense?
So you do 2 raised to the x over 2.
Huh?
You do 2 raised to the x over 2.
Yes. Because technically it's what? As when you change the square root to a rational exponent. It's technically what? What number? What fraction? 1/2. So 1/2 times x is x over 2.
How do you get the 2 the x?
Because this is basically 1/2. And then you'll have the x up there as well, and so we just multiply. Alright? Look at it now. Is there anything that doesn't belong? That doesn't look like something else, the rest? Huh? 4. 4 doesn't look like the others, because I got a base of 2 to the x plus 1, and I have a base of 2 raised to the x over 2. Is there a way I could rewrite 4 to have a base of 2? And what does this parenthesis mean? Multiplying. So when I'm multiplying with the same base, what do you do to your exponents?
Set them equal to each other.
You add them.
You add them.
You add them. Because at this point, we can't set them equal to each other because technically we don't have one number equal to another number. We have to basically condense this by adding our exponents together. And now by doing that, we can do what?
You just say x plus 3 there.
Yeah. You can cross out the 2's, and now you basically have x plus 3 equals x over 2, and it's a linear equation that we can solve for. Okay? The one thing that I think you guys have forgotten was that when you have a variable in your exponent, you're not allowed to use the calculator. The easiest thing is to get everything to have the same base. Because when you do that, you're able to apply your laws of when you multiply, you add your exponents, and then once you have one number equal to another number, you can cancel out your bases. Okay? That is the easiest way to solve an exponential equation. Multiply both sides by 2, making sure the x and the 3 get multiplied by 2, and x equals -6. But when you multiply both sides by 2, you're multiplying the entire side.
Right. And so 2x equals -6. And you would x equal -3.
Because you still have an x on that side.
Oh, okay. missed that?
Moving forward, exponential functions is in the form of f of x equals a to the x, where a is a positive real number and a does not equal 1. A cannot equal 1 or else you basically have a constant function. And then you have exponential growth versus exponential decay. One goes up, one goes down. Growth is going up, decay is going down. And one feature you should notice that if a is greater than 1, it's a growth, and if a is in between 0 and 1, then it's a decay. So you should know or have a general idea that when a is a whole number, like 3, 4, it's going to be a growth problem. But when a is a fraction, and a fraction that's less than 1, like 1/2 or 2/3, it's going to be a decay function. Okay? Now we kind of talked about this already when we were reviewing about exponential functions, but your domain is all real numbers. Your range is all positive real numbers. There is no x-intercept because there's an asymptote there. You have a y-intercept at 0, 1, and there's a special type of exponential function called that has a base of e. E is like one of those special exponential functions that also represents a growth, exponential growth. Now, of course, you're not going to say all real numbers when you are asked to do the domain. Okay? How should you write that? And what about all positive real numbers? Very good. Because it's definitely not equal to 0 because what's happening at 0? An asymptote. Okay, that's why there are no intercepts. And what's the equation of the asymptote again? Y equals 0. The y-intercept is at 0, 1, of course. Because think about it, if you have a base raised to the 0 power, x being 0, anything raised to 0 power is what?
1.
1. It will always be that way. Okay? And E is the base of 2.71828 and some change. Okay?
So if we have a function with E, it's
Always going to, yeah. Unless it asks you to leave it like exact, where it would do E to the number, but not actually have to do the decimal version. Okay? Now, will your domain always be all real numbers? No matter what the exponential function is, will always be all real numbers.
The domain of an exponential function.
True or false?
If they give you a specific range.
There could be an asymptote. There could be an asymptote. There
will always be an asymptote. But does that affect your domain?
I'm saying, what if there was like an asymptote? I don't know.
Like a vertical asymptote?
Yeah.
There's no possible way that you'll have an exponential function with a vertical asymptote.
Okay, so it's going to be all real numbers unless they give you a set.
Unless they give you a set domain.
Yeah.
What about your range? Will your range always be x is greater than 0?
Yes. It could be the other. It could be the other way.
Like x is less than 0?
It could be like.
I mean, y is less
your
than 0.
exponential could be in the negatives.
What will cause that to happen?
Reflection over the x-axis.
Exactly. Okay? Realize that when you have reflections over the x-axis, that's going to change your range. What else could change your range? Besides reflections. Which way? Down or up? What about left and right? Is that going to change your range? Will that change your domain?
Yes.
No. Domain's always going to be all real numbers. Okay? What about a vertical stretch or a horizontal stretch? Is that going to change your domain? What about your range?
Wait.
Actually, a vertical stretch is not going to change your range because all it's doing is just kind of pulling it in different directions. The only thing that's physically going to change your range is if you move it up, down, or you flip it. Okay? So, your transformations still apply to exponential functions. Okay? And this is how they apply. whatever your base is, and raised to the x power, if you have a plus k on the outside, it's going up. A minus k means it's going down. Okay? It's not in the exponent. It's actually like side by side with the base itself. But when your constant, or when your number's up in the exponent with your x, what does the plus k mean? Going to the left. And the minus means going to the right. So those still apply. Just like with quadratics, when you had parenthesis x plus 2 squared, it meant we move to the left. Same concept applies here. It's just now, instead of being in the inside parentheses, it's up in the exponent, which your variable. What about this one? A to the negative x. That's a reflection over the y-axis because you're making your x is negative. So in the negatives in front, that's going over the x-axis. And please, guys, be careful. All right? A is always a positive number. That negative tells you that it's being flipped over the x-axis. So if you're ever asked to evaluate, find A, say give me a graph or something like that, A is always going to be positive. The negative causes it to flip over.
Simply because it says the party name never gets
Unless it, well, let's see. The second to last one, what does that P mean? Horizontal or shrink by a factor of 1 over P. Remember, that's always the opposite. But the bottom one is a what? The number is true to itself. So yes, the transformations still apply. Do not forget about those. Hopefully you have them from the very first unit because we're going to see them. We saw them in quadratics, we saw them in exponentials, we're going to see them in circular functions, we're going to see them in logarithmic functions, okay? They apply everywhere. So when you look at the original function of 2 to the x, and then we have g, which is 3 parentheses 2 to the negative x minus 4. Minus 4. We got a lot of transformations. You can see in the graph kind of what's already happened a little bit. But if it asks you to describe the geometric transformations, that basically means list the transformations, what's happened. Okay? So, what's happened? One person, give me one thing. Down 4. Right 4. It's flipped over the y-axis, hence the negative up there, and then
vertical stretched by 3.
Vertical stretched by 3. All these things happen to form that graph. Yes?
More or less than that, they have to be in any particular order, or you just give it to
Well, if it just actually lists them, give it to them in any order. But if you have to graph it yourself, what do you start with?
the reflection and stretch.
Reflections and stretches first. Those can go in any order, but they have to be done before you ever move it left, right, up, or down. Translate it. Alright, so I want you guys to give this one whirl, graph it, and if you're like, well dang, how do I graph 2 to the x? You can always default to doing what to graph any function?
Chart.
Make a chart, make a table, okay? So if you need some assistance in graphing 2 to the x, make a table. And then use those points to do whatever transformations that is. So what happens to the graph of 2 to the x? To get g.
You got to move to the right too.
And we got to move to the right too. So the graph of 2 to the x using these points of this, not negative, positive 1, 4, 1 half, 1, 2, 4. I can even go up a little bit more, go 3, 8. I'm going to move every single one of these points over to the right 2 units. So this one gets moved over to the right 2. This one over here, right 2. Right 2. And make sure that your graph does not cross the y-axis. This gets very close to. Yours look like this, maybe a better picture. Questions?